Okay, for today I want to start talking about base change. We've talked about this briefly, but do you know that that can turn into that? I think it might help if I gave you an example. Let's say I had log base 3 of 5. I didn't make it work out nice, because otherwise you'd just want to call it like, oh, let's simplify it to 2 or whatever. So I made it some decimal that I don't know the answer to. Okay, well, first thing I want to talk about is it's got a base 3, but you can't add that to some other log that's got a base of like 4. So how can you change this base so that it's got the right base to like get along with another log? This is base 3. Somebody from looking at this will be able to tell me how I can make it base 10. That's pretty easy. Don't overthink this now. How can I make this into base 10 in the back corner? All right. And why didn't you say any base? It's base 10, and you don't need to say it if you're going with the common log, that's called. Okay, but did you know that I can use any base I want at that moment? All right, so if I want this to be base 4, I just put 4s there. It is that simple. I know that's not logical if you don't understand logs thoroughly, but let me help you understand it. Do you get that now that I just changed those bases from base 10 to base 4, the smaller the base gets, the bigger the answer gets. Both answers just got bigger, but you're dividing them. So they're staying relatively the same. The answer's going to be the same. It's kind of like, let's say I had 8 over 4. What's that equal to? 8 over 4 is equal to 2. Good. What if I make it, but what if it was 16 over 8? Still 2, because they both got bigger, but the ratio is still 2. So it's the same idea. What if I had 3 over 4? But what if it was 6 over 8? It's the same exact thing. Okay, so both numbers got bigger when I changed them to a log base 4, but when you divide them, you still get the same thing. So what's the moral of the story? I just changed from log base 3 to a log base 4, but I had to do it in 2 different logs. It's not quite as clean, you know what I mean? But that is in log base 4. So that's how to change something's base. All right, so let's say that you had something that was log base E, otherwise known as ln, and you wanted to add log base 2 of 5 to it. Do you get you cannot add them at this point? Because they don't have the same base. So, which one is easier to change to the other base? Well, it's actually, you could argue that you could change it either way. You could make this be log base 2 if you wanted. Or you could make this be log base E if you wanted. Which would you guys like to do? Should I change the first one or the second one? Which one? We'll change the second one. Or a bunch of people say second one. Let's change that to base E. Then do you get it's going to be log 5 over log 2. But wait, Mr. Server, that's base 10. So decide that it's going to be a different base and change it. What base do you want? E, so then this is log base E and log base E now. Yeah, I just changed each value, but when they divided, the ratio is still the same, so that's okay. And now they could be added. But this one has a denominator of 1, so it would be still a pain in the butt to add them. But at least they have the same base, so I could add them. But I'd need a common denominator, just like in all of math. If you have a fraction added to another fraction, they'd have to have a common denominator. So I have to times the top and the bottom by, in this case, log E. I'm going to say ln, though. Isn't that the same as log base E? Of 2 and ln 2. And yeah, now I can add them because they have a common denominator. And that got complicated. But hey, you're in honors pre-calc, so. All right. One last one. What's that if it was in base 12? called a change of base. So the first thing I always do is just write log 8 over log 7. And then I just try to remember that, oh yeah, what base did you want it to be? Base 12. So I'm going to put a 12 here and 12 there. If I have a bigger base, then both numbers are smaller than they used to be. But the divide of the two, because the ratio would stay the same. Yes?
So when you change the base,
yep. Yes. You can't just say, oh, now this is log base 12 of like 5. It's not that simple. Okay? Now, yeah. I'm going to leave it at that. Okay. Now there's another page in the slides that I really like because there are some really common mistakes that people make on tests. Like this yellow slide. Everybody find this slide. On number 1, do you see what the person did and then that's not right? What were they thinking they were doing? Yeah. So if the problem had a times right here, then that would have been correct. Do you see what I'm saying? So the question is, can you change something in the problem to make the answer be correct? Or, if necessary, change the answer so the answer is correct. Change one side or the other, because all of these, as they're currently set up, are wrong. Try to figure out what the person meant to do. Like, oh, they thought it was this. So on number 2, they thought that this 3 was putting everything to a power. And I already said that's wrong. So what could they have done with the 3? They could have put it in front. I agree. So if you want to change this and take that 3 out of there and put it there, that'd be okay. You get how that 3 could go down to the front? Okay. Option B, I was thinking if I were a kid and doing this problem, I would have thought, well, if the person wants to put parentheses around something, then they should have just put parentheses around the x and then put it to the third. That would have been right. Only the x is getting cubed. I would accept you do those modifications. Look at number 3. Try to figure out what the person thought and then what they should have actually done. I personally would have changed in the answer in this case. And it starts the same, but it looks way different than this. What should the answer have been? Kyla, what do you think the answer should have been? You are correct. Log base 10 of x was a good start, and then they should have put minus log base 10 of y. Okay. Number 4 is a classic mistake. They thought, oh, it's the whole won the argument thing. But no, they put a 0 in the argument. And that's just like reversed. It's transposition. It's like where things get reversed in your head. I understand that dyslexia is not quite that simple as just everything gets rearranged, but it's kind of like part of dyslexia. I've had students who were in this class and performed just fine who had dyslexia, but I know that it can be really also varying levels of like how hard it is on you. And one of the people that's famous I like to bring up, a lot of people don't know this. Have you guys heard of Richard Branson? He's one of the richest men in the world. He owns Virgin, all the Virgin stuff, like Virgin Airlines. Anyway, you'd know him if we were in Great Britain. He's like one of the most famous rich people in Great Britain. He like hangs out with Obama, and Obama goes yachting down to his place. And anyway, so Sir Richard Branson, he's a sir now also because he's that big of a deal in his country. He's also dyslexic. He barely made it through high school. And he's a self-made, not just millionaire, billionaire. and super like businessman. So the point is, even with dyslexia, that's not something that you should say, oh well, I can't ever amount to something. He was actually really not good high school student. I don't think that dyslexia like gave him a superpower or anything either. Also, the moral of that story is there's some people who are very good out in the real world that didn't do so awesome in high school. So don't let it make you think if you're coming out with a 4.2 GPA and you have an amazing ACT, that instantly means you're going to be super successful in the real world. And it also doesn't mean if you got a bad score in your math class and you aren't that good at school, you can also be super successful in the real world. So different skill sets. All right, and this one, number 5. What should they have done? They should have noticed in here that 5 should be moved. Where should this little 5 right here go? It's in the front of a log. Here, I'm going to blow it up. Maybe some of you can't see where it really is. 3 to the power of 5 log base 3 of x. Where could that 5 move? Up on top here to be a power on this x. And why would you care? Because then if I move it there, the bases are the same, so the answer's already there, and so that's the answer. It should be x to the 5th, not 5x. A lot of people see this and go, oh, bases are the same, so the answer's x. And then I'll just times it by 5, because I got to do something with the 5. You know what I mean? I could see that thought process for some kids. They know it's x, but they're like, what do I do with the 5? Well, it's in the front of a log, so it can be brought up as a power. Okay, I think those are good to look over. Common mistakes. That is one of the things I learned about good teaching is you find out through experience a lot of times what are the things that people commonly make for mistakes, and then you help people avoid them. All right. On this one, I have graphed 3 to the x. Why did I do that? Because they asked for the domain and range of it. If I graph 3 to the x, it's way easier to figure out its domain and range. So that's what I encourage you to do. Let's say on the test, we say, what's the domain and range of 3 to the x? Well, if you make a little sketch of it, this isn't that hard then. Domain that goes this way, right? How far does it go left and right? Well, forever, right? Would you agree that the domain of this thing would be negative infinity to positive infinity, or otherwise known as all reals? And here's the catch that you might not be thinking of. That instantly is the answer to the range of its inverse. Think about that. The domain of a regular function becomes the range of its inverse. You don't even have to figure out the inverse. I could. It wouldn't be that hard to reverse the x and the y and to solve it. You'd probably have to use logs. And anyway, but to find its inverse isn't that hard. But the best way to find the domain and range of this, which it looks kind of funny, is why I put the x up here, is to figure out the domain and range of the original. By the way, let's finish that off. What's the range of the original? Well, can't go below that dotted line. We talked about that earlier. And it can go forever up, so I'm going to say it's from 0 to infinity. Does that make sense to you? Now that I have the domain and range of the original one, don't I instantly know the domain and range of its inverse? Yeah. Its inverse's domain would be the range, and vice versa. So if I was talking about the inverse of this, I'd change that to range, and I'd change that to domain, and that's it. That's all I got to do. That's what inverses do. Their x and y switch, so the domains and ranges switch. Okay. I don't think these are that useful, so I'm not going to bother with that. You've done those before. This is a list of all the properties of logs. Is there any in here that you'd like me to explain further? Other than this one, because I've already talked about base changes. That's just changing base A to base 10. Is there any other of these log properties that you don't understand you want me to explain? You see the one where it's you won the argument? This one? How about the one where if the bases are the same, the answer's already there? That's this one and that one. All right. 12-minute warning is going off, so I better get you into your homework here soon. All right, so I do want to take 2 seconds to tell you what a slide rule is. It's based on logs, and we're in the unit called logs, right? So why not show you something that's got a log scale? Look for a second at these numbers on this little like strip, okay? And do you get that they are not equal-sized spaces? That is a log scale. Okay? In other words, instead of just numbering in order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you make them in a log scale. This distance here is obviously way bigger than like that distance there. Now, what that allows you to do is some kind of cool things, and I wonder who the first person is that figured this out. But it allows you to use a slide rule. It's a piece of plastic that's got a sliding thing down the middle, and you can multiply numbers with it. I'm going to show you a super simple example. Okay? And by the way, you might be like, why do I even care? Well, you might not care, but this was used to put a man on the moon. They literally used slide rules to do the calculations because they didn't have calculators back then. Can you believe we put a man on the moon when we didn't have calculators? We had computers, but they were like, you'd have to walk to the back, get the guy to put in this thing, and it was really complicated. And if you just wanted to do like 6.8 times 4.3, you don't want to stand in a long line of people to use the computer because they only had a few. I've mentioned this before. The amount of computing power that they had to put a man on the moon is way less than your iPhone. Your iPhone, together with all the computers that they had, your iPhone's more powerful. Way. Not even close. So they used these to do simple math when they were doing your calculations. The engineers would be sitting around. Think of this as a pointer instead of being a 1. You just line up that 1 with whatever you want to multiply. So I'm going to, remember, think of that as a pointer. So let's say I wanted to go with, I'm pointing at the 2. So I'm going to line this up right here like that. See, that's a pointer. It's not really a 1, it's just pointing at the 2. Then who can see how that's multiplying? What do you see? What do you see? Like that? You're right. How about this one? 2 times 3, 6. 2 times 4, 8. Everybody do 2 times 5 and then see how it's actually 10. It's pointing at the 2, right? That's a pointer. 2 times the 5 makes a 1, but it's on the next set, so that's a 10, not a 1. All right, I'm about to do 7 times. If I want to times by 7, where do I move my pointer to? 7. So that 1 is just a pointer, and I'll move it to the 7. There. So there, I'm pointing at the 7. So now that's 7 times 3 is, oh, it didn't work. Or did it? 7 times 3 is 21, so a little bit more than the 2, 21. See what I mean? How about 7 times 4? What should that be? 28. See how that's at about where 28 should be? And there was also little tiny lines in between. Like we have less lines in there where they were on a real slide rule. Everybody look at 7 times 7. What should 7 times 7 be? Very good. 7 times 7. If you look super close, you can see that I am slightly to the left of the 50, hence 49. All right, so anyway, that's a log scale, and 2 logs in action were used as a slide rule. If you go back like 2,000 years in China, you know what they were using? An abacus. They still had to do math, big numbers, especially if feeding a lot of people or whatever. You need to know a whole bunch of, like, oh, I got to figure out I got to give 10% of this grain to the guy next door. Use your calculator. except it's a bunch of beads on pieces of reed or whatever. The abacus. All right, so anyway, here's our homework, and right away you might be like, how is this at all related to what we've been doing? Well, isn't the argument a multiply problem? Couldn't you therefore separate it into two logs being added? So this would be log of, well, there's no base, Mr. Server. Well, then there is a base, and what is it? It's base 10. Log base 10 of 1.23 plus log base 10 of 10 to the 37th. Ooh, that's going to work out nice, because it's supposed to be expand and simplify, and I just found something I could simplify a lot. See what I mean? The thing I circled, what's that equal to? 37. So it's 37 plus whatever this decimal is. So I can get a pretty close estimate of what the actual answer is by doing that. All right, I want you to do problems 4, 5, 6. I just did problem 4 partially for you there. All right, on this page, I'd like you to do 18 and 19. On this page, I can live without you doing 30 and 31, so we're going to skip those. And here's just a reminder that, yes, in the movie Apollo 13, where they're trying to be accurate to history, they had people using slide rules at mission control. Like that, they actually did that to put a man on the moon. Not doing anything on that page, bottom line. This page, I want you to do A and B. The reason I'm cutting it down so much today is that we don't have much time left. Okay. That's all I have for you for today, other than you're going to Dropbox that little quiz that we corrected in class. And I just haven't opened the Dropbox quite yet, but I will in a second.